All right, everyone. My name is Sean Devine. I'm a technical sales specialist for ITM Instruments. Thank you for joining us today for this webinar via ITM University. Today's topic is going to be the importance of TO, carbon monoxide, and combustion testing with Testo. We kindly ask that you mute your microphone for the duration of the presentation. Our presentation will last about 40 to 45 minutes, and then we'll have time at the end for a Q&A. We encourage you to ask questions at any time. Simply use the chat feature and we'll get to your questions at the end during the Q&A period. ITM Instruments has been working closely with Testo for many years. We pride ourselves on being a leading distributor of Testo. This is a result of our dedication to offering you our product expertise, service, and competitive pricing. All right, so let's get started. Today's webinar is presented by John Fegan from Testo. John is a NATE certified instructor and regional sales manager for Testo. John has over 30 years of experience in working with instrument manufacturers to design, develop, and market instrumentation. His experience extends into the sales and training of instrumentation and to a variety of markets, including HVAC, weatherization, industrial, safety, and gas utility. John, we're very grateful to have you today. Please take it away. Thank you.
Well, thank you, Sean, and thanks everyone for attending the this seminar. I'm going to shut my camera off now and to the slide presentation. This happens to be a NATE presentation. It's on the importance of carbon monoxide and combustion testing. When we say NATE, we mean that it's a North America. Sorry about that. Hold on. It's North America Testing of Excellence, so it's actually worth 2 credits. And if anyone is NATE certified, they can get the 2 credits. And we'll talk about this later in the slide presentation. As I get into this here, hold on, I just want to, there we go. You saw enough of me already, but you know Testo. Hopefully everyone on here knows about Testo. We're a large manufacturer of combustion analyzers. Obviously, we're a German company. We're based in our headquarters in the United States or North America is in Sparta, New Jersey. One thing I want to stress on this is really the last bullet there. We're ISO 17025. I bring that up because 17025 is an international standard that we use for the quality, not only for the instruments themselves, but also for the service and the sensing capability of our instruments. Excuse me, sorry about that. Today's agenda, we're going to be talking about, again, it's a technical presentation on combustion. Nothing is on the instruments. Primarily, we'll go through the instruments in general, but combustion and CO safety, making good measurements, taking care of your investment, whether it's Testo's instruments or someone else's instruments, and really talking about the technology behind these instruments and how to take care of them. As I indicated, we're an international company, obviously, but in North America, our headquarters is in Sparta, New Jersey. We have about 40 people in our New Jersey headquarters. I'm a regional manager, as Sean indicated. I'm basically here in the southeast of United States. Actually, I'm in North Carolina. I'm sure it's a little bit warmer here. Today it's 50 degrees Fahrenheit, so than the rest of the country. But we do have combustion down here. A lot more air conditioning, but we do have combustion. So let's talk a little bit about combustion and why we actually test. You know, we're looking. There's some bullets here that show us that number one, it's all about customer value. We want to make sure that the systems, the combustion systems, the combustion processes, the residential furnaces, the commercial boilers are operating at peak performance, good combustion efficiency. We all are professionals in the field. We are known as the experts in the field, and we have to have an understanding of the combustion processes we don't have to be combustion engineers, but we do have to know the common measurements and the terminology and the operation of the combustion process. And this is what this presentation is going to talk about. We're also testing because of safety. A lot of OEM recommendations. Obviously, we want to meet those OEM recommendations for safe operation of the equipment, specifically on the CO issues, the carbon monoxide issues, and we'll touch base on that. Liability issues, certainly, we want to make sure that when we leave that appliance, whether it's a boiler, an industrial boiler, or a residential furnace, that we feel good about that we did the proper testing. We feel good about leaving that system in peak operating performance and safety. And also, it's also about profitability. We're here, all of us here today are here to make some money, and we want to make sure that we do the job right the first time. We don't want callbacks or any type of return to the customer because something's not right on the combustion process. So basically today, with the energy prices going up, oil prices, barrel of oil's going up today, a lot of things going on in the international markets, of course, but boiler tune-ups and energy assessment is very important. We'll talk a little bit about energy efficiency, how that relates to fuel savings, that the combustion efficiency provided by your analyzer equals fuel savings. We'll talk about carbon monoxide in general, CO, how it's CO toxic to the humans or to the operators or to the people in the building, and also possibly the dangerous fuel mixture you may have. Preventive maintenance scheduling, as you guys all know, I think you're doing more and more preventive maintenance scheduling. And then also environmental compliance. I'll talk a little bit about environmental compliance and how instrumentation today can help you with that. As you see here, this is a standard boiler, and we're mixing fuel and air together. This is a commercial boiler, of course. We'll also have some slows on the residential appliances, but this one happens to be a commercial boiler. And here is gases. This is what we're actually measuring. And when we measure the stack gases for oxygen, carbon monoxide, stack temperature, we're also looking at how this burner is operating. Our byproducts of combustion help us lead to issues with burner performance. And that's the big things with combustion analyzers, is that it's therefore energy efficiency, therefore combustion safety, and they're also used for compliance. Some basics on combustion: air, fuel, combustion products. You need a heat source to create combustion. So we have air and we have fuel. We ignite those two together. We have combustion products creating heat. Heat goes out the stack. Heat is also absorbed in our heat exchanger so that we can move that heat or boiler tubes, so we can move that heat throughout the building. Air is very critical, obviously, and as you probably all know, air, even in Canada, is 21% oxygen. So if we take a deep breath right now, we're breathing in 21% oxygen. The balance of that primarily is nitrogen. In a burner, whether it's a residential appliance or a boiler, we're doing the same thing. We're bringing in air, which happens to be 21% oxygen. And just like our bodies, we use the oxygen throughout our body. The oxygen in a burner is used to create the combustion process. It's very critical that we maintain the correct amount of air or oxygen going through the burner so that we have complete combustion. Fuel, I know you guys have a lot of gas up there. I know you guys have a lot of fuel oil. And then also we talked about the source of ignition. So we're mixing fuel and air together, and air again, 21% oxygen. And if you look at the top there, you'll see here the byproducts of combustion. Hopefully a lot of these formulas you already know already, but Carbon dioxide, which is CO2, is a byproduct of combustion. H2O is water, so we do have water. That's why combustion analyzers have water traps. We have stack temperatures or heat going out the stack. We want to try to minimize that heat because we really want the heat maintained in the boiler tubes or in the heat exchanger of the furnaces. Balance of oxygen. We use a combustion analyzer. We're sampling the flue gases. We're going to get a balance of oxygen because we're not using all the 21% oxygen. We're using 21% oxygen in the combustion process, but we do have a balance of oxygen coming out the stack, and that's important. We'll go through that in the next couple slides. Nitrogen, carbon monoxide, smoke. Carbon monoxide and smoke are in oil. Primarily, carbon monoxide is found in gaseous fuels as well as oil. Smoke is typically an indicator of poor combustion in oil burners. And then we have the two gases called NOx and SO2. This is nitric oxide. This happens to be sulfur dioxide. These are used on your large boilers. Maybe you're maintaining large boilers. This is for environmental compliance. So again, we're looking at air and fuel, creating combustion, and these will be the byproducts that you see coming out the stack. And what you see coming out the stack, we're able to measure that, and we're able to do some calculations. Two things you need to know is there's a term called incomplete combustion off to the left, and a term called complete combustion. Complete combustion means that we have enough air to support the combustion process. Therefore, you can see here we have a balance of oxygen in the stack gases. So if you're using a combustion analyzer, hopefully it's a Testo combustion analyzer, you're able to measure oxygen at around 3, 4, 5%, maybe higher on residential gas furnaces or oil furnaces. That's good because if you get too low, if you don't have enough oxygen, what you can start producing is high concentrations of carbon monoxide. So when we say complete combustion, what we mean by that is we have enough air to support the combustion process. We have what we consider a lean mixture, and we're not producing high concentrations of carbon monoxide, and we have good efficiency. When we have what we call incomplete combustion, that means we have too much fuel and not enough air. When that happens, we have incomplete combustion. We start producing high concentrations of carbon monoxide. In oil burners, we'll produce both CO and smoke. So we want to try to avoid, obviously, the incomplete side of the combustion process. We always want sufficient air to operate our burners. So let's go to this little graph here, and it may be a little complicated here at first, but I'll take this step by step. It's important that we know the relationships of gases in the flue gases. The reason why is instruments today, whether you use a Testo or someone else's, is a quite easy instrument to use. You can turn it on, it goes through a power up, it does its own checkout of the instrument, and then when you're ready to go into the flue gases and look at the readings, you're going to get a lot of these readings simultaneously. And I just want to go through some of these readings with you. If you look at this combustion diagram, we have two sides of it. Incomplete, which we just talked about, which means excess fuel. On the complete side, we have excess air. So what we're saying is we want to stay on the complete side. And as we add more and more air to the burner, or if we adjust the air and fuel ratio and we add more air, what happens to the O2 in the flue gases? Well, it's going to go up. Conversely, carbon dioxide, which is an inert gas, and we see both CO2 and CO2 on the complete side and on the incomplete side. But CO2 is a byproduct of combustion. You're going to see CO2, carbon dioxide, in percent CO2. So as we increase our air in the burner, if you're looking at CO2 on your instrument, it's going to go down according to the amount of oxygen that is added to the burner. CO2 is found on both sides of the curve, but you'll notice here that oxygen is not present on the incomplete side, which means that you have too little air and excess fuel. Carbon monoxide, another measurement that we measure, very important measurement because carbon monoxide is the toxic gas. It is a dangerous toxic gas, but we minimize it in our combustion process going out the stack. So on the excess fuel side, you'll see that the carbon monoxide crosses over into the excess air side, but it's at low concentrations. As we add more and more air, then we're away from the higher concentrations of carbon monoxide. Now, if we go too far excess air, what happens is that curve of CO comes back up. Reason why is we're cooling down the flame temperature. So there's a section here where we want to operate our commercial boilers. And we want to operate these boilers, and I'm saying boilers, I'll talk a little bit about furnaces later, but boilers operate with between maybe 3% oxygen to 6% oxygen, high CO2, good combustion efficiency, and a trace of carbon monoxide. This is typically in gaseous fuels, okay? So on residential furnaces, we're usually farther away from the carbon monoxide line. So we're sacrificing efficiency, but we have very safe combustion process because we minimize the CO, the carbon monoxide, down to maybe less than 10 ppm, 15 ppm. A typical commercial boiler operates around 100 or less parts per million going out to stack gases, okay? So if you look here, if we're moving this way, if we adjust the air and fuel, we're moving to the right, you'll see that oxygen goes up, CO2 comes down, we start losing efficiency. This here, called the stoichiometric line, separates incomplete and complete combustion. It's also an area where we have a pretty high combustion efficiency rating, but we don't want to be here because of high concentrations of carbon monoxide. If we reduce the air in the burner and we happen to pass over into the complete fuel-rich mixture, then we really have some serious issues. We have high concentrations of CO, and I'm talking thousands of parts per million of CO. We have no oxygen. Our instrument, our combustion analyzer, may be measuring 0 or 0.3, 0.5% oxygen. And like I said, typically, you're measuring 3 to 6% oxygen here, and maybe higher on the residential furnaces, 7 or 8 or 9% on the residential furnaces. So here's a relationship of the gases. And oxygen, stack temperature, and carbon monoxide are measured with sensors. Carbon dioxide is calculated based on knowing the fuel, and so is the combustion efficiency. It's calculated based on knowing the fuel and the oxygen. That's why when you turn a combustion analyzer on, you always need to select the correct fuel, because we not only are measuring CO and oxygen and stack temperature, but we're also calculating CO2 and efficiency, which requires the correct fuel to be inserted into the instrument. Here's the measurements that we measure: net stack temperature, oxygen, carbon monoxide, draft. All these sensors, all these are sensors that go into an analyzer. We do the calculations too. We can measure oxygen temperature and know the fuel, and we can calculate the combustion efficiency. We can calculate carbon dioxide and other emission values as well. So when using a combustion analyzer, test in, test out. Always check carbon monoxide in the area of the combustion process. Document your work. Most of these instruments today have the capability of Wi-Fi, send it through the internet, or printing capability. You can print or store information in the instrument. So, there's things that we can control. We control variables in the combustion process, and this pressure is a measurement that we measure to measure pressure, the fuel pressure, as well as draft in the stack. We do a calculation called excess air. We measure temperature and through a thermocouple that's at the probe tip. We also measure the ambient temperature. We can measure pressure not only from a positive side, but a negative side. So we can measure the draft. Percent oxygen is very important. We talked about complete combustion. We need to see oxygen when our probe is in the stack. Carbon dioxide percent is a measurement, or is a calculation that we do. Carbon monoxide, CO, is the gas that is the result of incomplete combustion. That's a deadly gas. So don't get percent CO2, carbon dioxide, and carbon monoxide mixed up. They're two different formulas. One is very toxic, like carbon monoxide. Carbon dioxide is a combustion byproduct. And then the combustion efficiency is the heat available and how well the fuel is being mixed with the air. So when we're doing, like I said, combustion analyzers can be used for ambient CO testing. I'll talk a little bit about CO testing in the next slide, but it's important that if you're doing residential, light commercial, and even commercial, industrial, that we're measuring the room air of carbon monoxide. We want to make sure that there's none of the byproducts of the combustion process are going into the boiler room or the home, and that certainly includes carbon monoxide. Right? Draft is another measurement that we do in the analyzer. We measure draft to support the combustion process to make sure that we have the right amount of draft pulling the flue gases out the stack. If we have too high of a draft, then we can pull the heat we can pull too much heat from the combustion process. If we have too little draft, then we could start having backdraft and flue gas spillage, and certainly that's not a good thing when in a home or a building. So let me just talk a little bit about carbon monoxide. We measure carbon monoxide in parts per million, level. Any combustion process, any fuel can generate carbon monoxide, and it is a toxic gas. Our burners, our boilers, our furnaces are designed very safe. They are designed to minimize the carbon monoxide, to make sure that carbon monoxide, the flue gases are going out the stack at the right velocity, so that we don't have any issues with people that are in the building. So the furnaces and the boilers are designed safe. It's our job to maintain the safety of these furnaces and boilers by checking carbon monoxide. That's one of the critical measurements for combustion safety. And here in the United States, and I don't have too much data on Canada, but here it's just an idea of what is in the number of deaths per year in the United States because of combustion processes. You'll notice too that it really is. I live in the South, and a percentage of issues of carbon monoxide are more in the South than in other parts of the United States, like the Northeast, where we have a lot more heating appliances. And the result of that is we're not in the Southeast here. We have such a short heating season, and a lot of the service technicians and contractors don't use carbon monoxide measurement. They're looking at furnaces and boilers. Commercial guys do, but on the residential side, we're not doing very much combustion testing. And as a result of that, we have a very high percentage of fatalities in the United States per year. Keep in mind that carbon monoxide is a formation of too much fuel, not enough air, and it's CO. Again, CO2 is a totally different type of gas. And the reason I'm bringing carbon monoxide up is it is not only is it poisonous, but you can't see it. you can't smell it, you can't taste, and it mixes very well with the air, which means that it follows the air currents in a home and building very well. You could have an automobile outside with a garage door open, and the automotive exhaust, which have high concentrations of CO, could make its way into the home and set off a home alarm or so. But it mixes very well with air, carbon monoxide. It follows the air currents and the pressure differences in the home. And what you can see here is as you're exposed more and more to carbon monoxide, the symptoms of carbon monoxide get deadlier and deadlier. And what that's a result of is, we're breathing in CO and oxygen, and instead of the oxygen being picked up by our red blood cells, the carbon monoxide is picked up instead, and we're not getting the oxygen to our major organs, which is where you get these symptoms here: headaches and blurred vision, fatigue, drowsiness. So, and then maybe if you go outside, you start to feel fine because now you're away from the CO, you're breathing in fresh air, and you're diluting that carbon monoxide. So one thing about it is too, you'll notice that in the heating season, which is now, especially where you guys are located, these symptoms kind of mimic the flu-like symptoms, probably the COVID symptoms as well, but sometimes this is misdiagnosed as a flu, where you have an issue with carbon monoxide. ppm carbon monoxide, we measure it down to 1 ppm. That's why the CO cell sensor is calibrated periodically on a concentration of carbon monoxide. Typically, you can measure down to 2, 3, 5 parts per million CO. And it's important to do that because we're using these analyzers in the flue gases, as well as they can be used in checking ambient air conditions. And as we talk about ambient air conditions, the CO effects, things of that nature, you can see here that low concentrations of carbon monoxide, you can start experiencing the symptoms of carbon monoxide at 200 ppm, 400 ppm, 800 ppm. And this is typically on people that are very healthy. So a ppm is a very small concentration. And when you get into 200 ppm, you get a slight headache in 2 to 3 hours. The concentration increases, the exposure rate increases, the symptoms also increase very rapidly. So 12,800 ppm is equal to 1.28%, if you want to convert that to percent. And that's why we don't look at carbon monoxide in percent by volume. We measure it in ppm, parts per million, 1 out of 1,000 parts per million. So, oops, sorry, wrong way. So here's some ambient air conditions. This is ambient air conditions, as I indicated to you previously. Typically, furnace burner manufacturers want to maintain no more than 100 ppm. You may have some local protocols, but 1 to 9 ppm, 10 to 35 ppm is moderate. These are ambient air conditions. When you get into over 100 ppm CO, that's a very dangerous possibility. You got to evacuate the home immediately. NOx is another parameter that we measure. NOx is an environmental gas. I'm not going to get too much into this, but it is an environmental gas and it contributes to our pollution, acid rain, ozone, smog. EPA here in the United States regulates NOx, not so much on the residential side, but on the commercial side, industrial side, and we measure NO and NO2 in our combustion analyzers as well. So, this, when you get into measuring NOx, this is a third sensor that you would need. This is where you're in the larger industrial processes. Some of you may be doing that, and you're measuring NOx to maintain NOx in the single digits. And again, NOx is a toxic gas. It's more for environmental safety and pollution, and it's measured in parts per million, just like a carbon monoxide sensor. The last thing here is combustion efficiency. We're checking we got the probe in the stack. We're pulling out the oxygen in the stack. We know the stack temperature with a thermocouple. We got the fuel that we know, and we can calculate the combustion efficiency. And the whole thing with combustion efficiency is fuel savings. So if you look at this graph here, and this is just an illustration that if you start at 75% and you can increase your combustion efficiency to 80%, you're saving roughly $63 on $1,000 of fuel spent. Now, this doesn't apply very much for residential appliances, homes. But where you get into the combustion efficiency is where companies are spending huge amounts of money, dollars, Canadian dollars, US dollars, whatever it may be, on fuel cost. So this is where you get into the big numbers where hospitals, universities, industrial factories may be burning millions and millions of dollars of fuel a year. This is where they want to make sure that not only they have safe combustion, but they also want to have good combustion efficiency, because the fuel savings is going to be in the hundreds. It could be in the hundreds of thousands of dollars. And again, what we're measuring is oxygen, temperature. We know the fuel, and we can calculate the combustion efficiency. It's a calculation that we do. Now, I do know you guys have a lot of oil burners up in Canada. Here in the Southeast, we don't, but we do have it in parts of the United States. And I work a lot with Beckett, and they're as you know, they're a US manufacturer of burners. They have a way of they have 4 basic steps for using a combustion analyzer. Number 1 is they want you to find a trace of smoke first. And how we find a trace of smoke is using not a digital instrument, but a smoke pump, similar to a bicycle pump, where you're pulling in flue gases through filter paper and matching that filter paper up to a scale. Then from there, you measure oxygen or CO2. So what you're trying to do is you're trying to find a trace of smoke at 1, and you measure this oxygen at that point using a combustion analyzer. Then you open up the air shutter, and when you do that, you're going to increase the air by 1%. And this is going to leave you at a very good combustion efficiency and also leave you at a 0 smoke. If you didn't get that part of it, here's a diagram again. The diagram I showed you previously was mainly natural gas, but in this one I've added a smoke line. What Beckett here in the United States is saying is check the smoke first. Make sure you have a trace of smoke, which means you're not way up here at an 8 or 9. You're down here at a 2 or 1. So once you get that 1, let's say, then you use a combustion analyzer and you measure at that point, and you may get 4.5% oxygen. Beckett is saying, now increase that oxygen from 4.5 to 5.5. So if we do that, we're away from the smoke line. We got a 4.5% oxygen. We're high in the CO2, and we still maintain good combustion efficiency, which means we have safe operating appliance. Couple recommendations here. And these are typical readings. Again, these are not Testo readings. These were put together by a number of manufacturers, OEMs that we contacted. And these are some typical readings on oil-fired power burners. And again, I like to stress that these are typical readings, ballpark readings. You need to follow the manufacturer specifications. They're the experts on their equipment. So you see here the oxygen readings on cast iron cone, flame retardant, carbon dioxide reading, the temperature readings in degrees C here, draft overfire, And then here's your carbon monoxide reading, which is less than 50 parts per million. So gas-fired power burners, 3 to 6% on oxygen, carbon dioxide readings, stack temperature readings between 135 and 300 C. Inches of water column, draft, less than 100 ppm CO on the carbon monoxide. Draft-induced gas-fired burners, again, here are some areas. Now, you may have your own specifications on this equipment already, but again, it should be somewhat close to what you see here. Again, this is done by a survey of gas and oil burner manufacturers and what they recommend on their burners as far as combustion efficiency and the measurements of flue gas. Now, as far as boilers itself, getting into larger boilers, in sampling, you want to your probe tube has to be below any type of draft diverter, has to be right above the breech of a boiler so you can pull in the flue gases. So there's no dilution. If you're above that draft diverter, you can get a lot of dilution here, causes readings to be exaggerated a little bit. Usually a 1/3 to 1/2 penetration into the stack. There are probes out there that we have that are much longer than the standard length, which is roughly 1/2 meter or so. Sampled during the different fire rates. The key is to tune the maximum efficiency and make sure that your carbon monoxide is low, and follow the manufacturer's specification. Here's an atmospheric warm air furnace. Again, where you're going into the heat exchanger tubes, checking CO around the burner area, check fuel pressure, check carbon monoxide, again, around, not only in the flue gases, but also in the area of the combustion zone. Here's a condensing furnace here, going out into the stack for combustion efficiency, sample around the burner for carbon monoxide. Sometimes you can go into the stack termination if you're doing carbon monoxide measurement, but when you're doing combustion efficiency, you need to be near the combustion process, closer to the combustion process. And then, we get into some of the instruments and the tools. You'll see that, with the standard combustion analyzer today is a digital thermometer. We use type K thermometers. We have pressure sensors in these instruments with Testo. A pressure sensor, a draft sensor is a standard measurement that we do. The instrument has a calculated combustion efficiency. It measures carbon monoxide, both in flue gas and room air. And all instruments, I believe all instruments, by all Testo's instruments, have the capability of printing, storage capability, and converting to a PC or an app. Now, on a combustion analyzer, probe and hose assembly could be several feet long. Your hose could be 7, 8, 10 feet long. Maybe you're using a hose extension. We can do that. The probe tube here is around 12 inches. Convert that to metric, but you're pulling sample of flue gas from the stack gases through a probe assembly with a filter on it. Then it goes through a water trap. From the water trap, it goes internally into the instrument. And then the last place that the flue gas goes before it's exhausted out of the instrument is to the sensors. So it's important that we have a tight seal between the probe tube that's in the stack all the way to the internal plumbing of the instrument. If something happens to be disconnected, or if there's a crack in the water trap, or if the particulate trap cover is not tightened, and we get excess air coming in here, we're diluting our flue gases. Remember, our flue gases in here are 3, 4, 5, 7% oxygen, carbon monoxide, very little, hopefully carbon monoxide, as if air comes in through our hose assembly somehow, then we're bringing in that fresh air at 21%. We're diluting our oxygen, therefore creating not a very accurate efficiency rating, if you get that. So I'm really just saying, maintain your probe and hose assembly, make sure there's no cracks in it, no leaks, anything like that. Flue gases, combustion analyzers are good for combustion efficiency and safety and compliance that we talked about. Ambient CO testing. It does have pressure sensors in. Not all instruments have pressure sensors. Testo's does, but you can use positive pressure. We got negative pressure. We got dual pressure in our instruments. And then you can have not only one temperature probe for one in the stack, but you can also have another temperature probe in the primary air or in the primary air. Looking at the instrument themselves, the basics of these, most of these instruments are lithium-ion battery packs, power supplies. This happens to be the inside of a Testo 300 here. And you'll see these are the sensors which are replaceable in the field. Be careful with very cold temperatures, especially up north, because you don't want to freeze anything in the instrument. When you start to freeze, it has an impact on the sensors, on the LCD display, certainly on the batteries. If you do have water that's not dumped out of the water trap, that could turn to ice and crack the water trap. So make sure that you keep this in it. I say 0 degrees Celsius. Typically below that, you get into extremely cold temperatures. And another thing that happens too is keep in mind that if you take this out of a truck and it's very cold out and you go into a warm boiler room or a warm home, you may create some condensation because you're going from a cold environment to a warm environment. So you'll have some condensation, and water on PC boards is not the best thing for analyzers. So water traps need to be maintained, cleaned. Again, air tightness is very crucial. Particulates and filters need to be dried and cleaned. Anytime you have a filter and our filter is in the probe assembly, there's a white filter or a yellow filter here, and it turns black from the inside out. So if you have a black filter, it's time to change that filter. Oil has more particulates and gas, so you may be changing the filter more frequently with oil. Quick disconnect here allows you to connect the instrument with one probe. Internally here in this probe attachment is a thermocouple connection, the flue gas hose, and also the draft hose. They're separate hoses. Measures, very accurate, like I said, very accurate CO measurements. We do down to 1, 2, 5 ppm, and periodically, and we maintain that once a year. Your carbon monoxide sensor needs to be calibrated. One thing about carbon monoxide sensors, so that they do go, they are very sensitive down to 5, 10, 15 parts per million, is if you overrange the sensor, in our case, if you go over 4,000 parts per million, you could actually damage that sensor. It's not designed to see 4,000 ppm and above. Typically, and you can adjust the instrument in most cases to shut off when it sees 2,000 ppm. Again, let's keep in mind that we're measuring hundreds of ppm or less. We're not measuring thousands in the flue gases. We're certainly not in ambient air. So if you have an instrument and you're reading heights 1,000 ppm CO, pull the probe out immediately, because you have a condition that it's going to take some time to figure out why that CO is so high. Pre-calibrated sensors are a big deal today, so they're plug-and-play type sensors. We recommend once per year on our sensors to be calibrated. This is the toxic gas sensors here. Self-calibration on the O2. What that means is that every time you turn your instrument on in fresh air, your instrument is calibrating that oxygen sensor to 21% oxygen. That's why it's so important to keep in mind that 21%, because you're going to see that a lot on your instrument. As soon as you put that probe in the stack, your instrument should be reading 21% because it was just calibrated in fresh air on 21% oxygen. A couple things about sensors before we come to a conclusion on this. Sensor life on sensors today have improved dramatically over the years. Today we have at least 2-year warranties. A lot of our instruments also have four-year warranties on sensors. As long as you don't blow past the range of the carbon monoxide sensor, you can get at least 4 years on your CO sensor. Thermocouples, sorry about the degrees Fahrenheit there, but thermocouples are good. We have thermocouples that go up to 2000 degrees Fahrenheit. Our typical sensors go to 1000 degrees Fahrenheit. You'll see too, what's unique with Testo is that we have one connection. So that when you plug that probe hose in, you got a flue gas hose here, you got a draft hose here, and you got a thermocouple connection here. And when you have a hose like that, you have less likely for cracks and issues with leakage or anything like that on the hoses. Pumps, feel replaceable. Most analyzers, I can't speak to all of them, but most analyzers you can do the repair yourself. Printers are very popular. They're now Bluetooth printers. We have the Bluetooth printer. We also have a blue Wi-Fi, so you can transfer the data from a phone and a tablet to through the internet. Cases, carrying cases, Wi-Fi connection, magnetic boot. Keep it in the carrying case. Again, sensors, carrying for your instrument here. This happens to be a 2-gas analyzer, oxygen and CO. Pressure sensors over here. Battery packs here. This has to be a lithium-ion battery pack. So again, the calibration of the CO sensor is typically once a year, where we put a known concentration of CO on the sensor, and it has to be within the specs of that, which is plus or minus 5 ppm. Oxygen, on the other case, every time you turn the instrument on, we're calibrating the O2 cell to the fresh air, 21%. Okay, trying to lower the cost of the ownership in these analyzers. Probe and hose assemblies we talked about. Plug-in hose, extensions. You can go, in some of our instruments, you can go up to 25 feet. Hose extension. Ambient CO, you get other probes you can attach to it. Our water trap is on the bottom of the instrument, and you can visually see the level of water, and there's a spill valve here. So you open that spill valve up, you dump all the water out. You want to do that after the test. There are some fill lines on here, so that if you're holding the instrument upright and you surpass a fill line, it's time to dump that water out, because you don't want to pull water into an analyzer. Here's some tips. Again, mechanical room and stack gases, sample both. You got a lot of things you could do, not only with combustion efficiency, but you got delta T. You got delta T. You got probe. Know your probe location. Know the relationship of those gases. Have an instrument that prints and stores the data, because you want to be able to pull that up at a later date. Instruments are designed to run very accurate sensors. Testing. When I say steady state combustion, make sure the boiler's warmed up. Make sure you have an accurate CO sensor. We have NOx filters that guarantees the best accuracy. Again, don't overrange your sensors. Check water traps. Some typical service tips on combustion analyzers. One thing about combustion analyzers is it depends on what market or what your application is. A residential combustion analyzer is mainly for residential furnaces, oil and gas furnaces. You get into our professional series, you get into a commercial grade. And then we have what we call an industrial grade, which has a high carbon monoxide sensor in it and also a NOx sensor. So you got really good, better, best. and it's based on the pricing, and ITM can do a better job with pricing than me on the Canadian side. But pricing is, this happens to be one of our, what I consider a residential analyzer. That's going to be the least expensive. The middle range analyzer and the top line is basically what I'm talking about here. So, Sean, are you still there?
Yeah, hey, I'm
Hello?
still there.
Okay, good. Thought I lost you there.
Yeah, no worries. Are you, John, is this the end of the presentation here?
Say that again, please.
Sorry, John, are we at the end of the presentation here?
Yes, we are. The only thing I have is the NATE certification on this next slide. And if you see that slide, all you have to do, if you're NATE certified and you want a couple credits, which is a accredited course, all you do is send it to my email address, your name and your NATE ID number. And my email is jfigan, F-I-G-A-N, @testo.com. And that ends my side of the presentation, Sean.
Perfect. Well, thanks, John. That's great. Very informative. I know I learned a lot myself. Everyone, it's now time for us to take advantage of having an expert like John with us to answer any and all questions you may have. So to send in a question, please use the chat feature. And please note, if there's any product-specific related questions, such as pricing and availability, we encourage you to visit our website, itm.com. There you're going to find a list of the products, pricing, tech specifications, as well as all our contact info, so the different ways that you can connect with our technical support staff. And we'll be happy to address any and all questions you may have. So John, we have a few questions that have come in. Joel is asking, what is the biggest factor for soot formation in a natural gas-fired commercial boiler?
Soot is the result in a natural gas-fired burner, did he say?
Yes, exactly.
Okay, I mean, typically you're going to see the soot in oil burners, and that's the result of smoke. Smoke is soots up the heat exchangers, the stack. It's the internal of the stack. As far as the natural gas fuel, I have had very little information on the soot buildup on natural gas. It's primarily with oil, and that's a result of the smoke that's caused by the burner itself.
Perfect. No, I think you got it there. Student is, he's a home inspector. He doesn't need to perform any complex testing. What would be the best device to detect natural gas and carbon monoxide? So I'm assuming it wouldn't be a combustion analyzer, right, John?
Yeah, if he's looking to go into the flue gases, he's a home inspector, and he's looking to go into the flue gases to check carbon monoxide in the stack gases, that requires a combustion analyzer that with a probe and hose assembly that's capable of high stack temperatures. If he's only looking at ambient CO, he can use a combustion analyzer, but ITM and Testo has carbon monoxide ambient air testers so that you can just check the ambient air near the combustion zone in the living area of a home, but you can't go in the flue gases with an ambient CO detector. You still need a combustion analyzer. As far as combustible gas, there are, and Testo makes them out there, but there are leak detectors, which measures natural gas, propane, any combustible gas, which is a meter or an instrument that gives you an audible sound and tells you by the audible sound whether you have high, a concentration of or a leak of natural gas or propane or any of the combustible gases. So a combustible gas leak detector, a CO ambient instrument if he's not going into the flue gases, or a Testo 310 if he needs to know to go into the flue gases.
Perfect. Yeah, that's there, Stephen. For that, it sounds like we may need to talk a little further on which product specifically will work. Off the top of my head, the Testo 316 seems like it would be a good leak detector for you, but definitely something. We'll reach out to you by email, and we'll discuss back and forth to make sure you're looking at the right product. John, so we have another question here. Mustafa is asking, does the 21% oxygen vary at all ever on certain locations, like a versus a high rise?
Well, it's always good to calibrate turn on your instrument in the area that you're testing. Because if you get into higher pressures, if you're in an elevated area, a higher altitude, you need to calibrate the oxygen sensor at that location.
Perfect. Now we have, sorry, here just a couple questions coming in at once. Ivan is asking, what is carbon monoxide air-free?
Good question. Carbon monoxide air-free is a measurement that we do and others do. It's a combustion analyzer that measures carbon monoxide and oxygen. And carbon monoxide air-free is subtracting out the effects that the oxygen has on the carbon monoxide sensor. What I mean by that is that in flue gases, you have, let's say you have 50 parts per million CO and 5% oxygen. So what carbon monoxide air-free means is, what if my oxygen was zero? Air-free is zero. What would happen to my carbon monoxide? Well, it'd be much higher. And it's a calculation that we do in our analyzer that takes out the dilution factor of that oxygen or air, if that makes sense.
Okay, yeah, I think I follow there. And Ivan, if anyone needs any clarification on these questions, please feel free to contact us directly, and we'll be happy to expand on anything further. I'm just going to try to get through the last few questions here before we wrap things up. Zachary is asking, and this is interesting for me as well. He recently bought the Testo 300. Is he able to use it as a manometer? Because his Testo 320 had that feature, and he was curious if it's still available on the 300.
Yes, he does. There's two ports. There's a negative port on the 300, and if you look at the probe assembly itself, there's actually two hoses in that probe connection. One is for flue gases, the other is for pressure. So differential pressure using his 300 analyzer, and that's a test. That's a test that he can scroll through to go to measure differential pressure. Again, if he needs clarification on that, we can help you, Sean, with the explanation. But yes, you can do two pressures simultaneously, positive and negative.
Okay, good to know. I didn't know that one, so that's great. Robert, I see your question here about working on a Navian NCB 240E. I think, Robert, what we'll do, we're going to email you after this, just because it seems like it's a more detailed question that John and I will work on. So Robert, we'll get in touch with you shortly. If Anthony is asking, when finding an appliance that has low efficiency, high carbon monoxide, do you first look at the air side or the fuel side?
Well, it depends on the type of furnace it is. The first thing that a lot of contractors will look at is the fuel pressure, making sure that the fuel pressure is correct going into the burner itself. And typically on natural gas is around 3.5 inches water column. Sean, do you do water column, or do you do another unit of measure for draft?
Water column is one of the more popular ones. Like I see, I think H2O, same thing, or very close.
Yeah, inches water column. But typically on a residential appliance, fuel pressure is very important, and that's stated by the manufacturer. Most manufacturers on natural gas applications is around 3.5 inches.
Okay, perfect.
Water column.
All right, I'm sorry everyone, we are running out of time and there are quite a few questions here. we're going to try to get back to everyone, but we do need to wrap things up. I'm sorry, so please, any questions, if you could email info@itm.com with any questions you have, we'll be happy to get right back to you. And otherwise, we will be reaching out to you regardless after this presentation. To close things off here, on behalf of ITM University, we want to thank you for attending our webinar today. We hope that you found it informative and helpful. ITM Instruments is available to assist you in any way. Simply visit us at itm.com. ITM.com, you're going to have access to the entire list of Testo products with all descriptions and specifications. You're also going to find our contact info in order to contact us and connect with any of our technical support staff who are able to answer any and all questions that you may have. At the end of the webinar, we're going to be sending you a very short survey for you to complete because your feedback will assist us on improving and allowing us to bring you more topics that are of interest to you. We're also going to be emailing you instructions on how to claim your NATE credits for attending today's webinar, what John was speaking about before. We do have upcoming webinars in the next few weeks and months, so please visit the training section on itm.com for a full schedule of the upcoming webinars and topics. And don't forget that as a thank you for attending our webinar today, your name will be entered into the draw to win $100 for your next online order. The winner will be announced on our social media channels, so please be sure to check us out there. Again, sorry that we couldn't get to everyone's questions. We'll be happy afterwards. John, I want to thank you so much for the informative presentation today. I think we all learned a lot, and it was very appreciated.
Again, thanks everyone for attending, and thank you, Sean, for your excellent organization.
Perfect. Thank you, everyone. Have a great day. Take care.